The Ben Heck Show is brought to you by Element 14, the electronic design community where you can connect and collaborate with top engineers from around the world. Join now at element14.com. What a great day for a hike. The birds are chirping, the alligators are smiling, the sun is out, the air is super fresh, and there's plenty of indigenous roots and berries to eat. Although I kind of wish electronics were involved.
That sounds like a job for geocaching.
Who are you? Some sort of disembodied voice inside my head?
Nope. I'm one of the guys that writes Wikipedia.
Oh, those people. Okay, what is geocaching? Some sort of trade-in program for 1980 Chevys?
No. Geocaching is an outdoor recreational activity.
Outdoor, recreation, activity. Not sure I like where this is going.
Participants can go on GPS-guided treasure hunts.
I like treasure.
On this hunt, they can find boxes called geocaches.
What are in these geocaches? Treasure?
At each geocache, you can electronically sign the box and receive clues to find the next one.
Oh, so the real treasure is knowledge. This could be a fun project for the show, where you can make an electronic geocache that can be left in the woods for days, weeks, or maybe even years. Let's get started.
Amazing hacks.
How can we make this portable?
Inspired designs.
I am the internet troll.
Regrettable acting.
Batten down the hatches!
Each week, Element 14's The Ben Heck Show brings you innovative projects using electronics, engineering, and more.
Here's my plan for how to put together the BeagleBone Black geocache. First, we need something to put the geocache in, so I'm thinking some sort of pelican case, a really obnoxious color like orange or yellow, so it's easy to spot in the wild. We'll use the BeagleBone Black inside of it like a miniature laptop to log images of the people visiting the geocache, and there'll be a keyboard to log, hopefully, a friendly message. But we want it to be out in the wilderness for quite a long time, so we're going to need some sort of low power circuitry for it. I'm thinking what we'll do is we use an ATtiny. It'll be asleep most of the time, but when you type in a code, the ATtiny microcontroller will wake up, and if the code is correct, it'll activate the BeagleBone Black. Since that is the high current device, it'll only be on when someone's actively using it. We're going to shoot for at least 1 month of battery life. We'll have a BeagleBone Black and a camera in the top half of the case. The bottom half will have the keyboard, the code keys to wake it up, a battery pack, a power converter to turn the 7.4 volt battery pack into 5 volts, and a microcontroller to do the power regulation. So here's the sequence we'll use. The ATtiny will continuously look for a code on the code keys, and when buttons aren't being pressed, it'll sleep and the buttons will wake it up. Once the correct code is entered, it'll power up the BeagleBone Black. The BeagleBone Black will then do things like take your photo and take messages. Once you're done with that, the BeagleBone Black will turn itself off automatically. The ATtiny will be able to see that the BeagleBone Black has shut itself down. Once that happens, it will power off everything, that way it doesn't take any current, and then go back to sleep waiting for a code. We need a safe, non-logic level way to activate the latch solenoid on our circuit, because when the BeagleBone Black's ground gets disconnected, the pins tend to float. So what I think we're going to do is use an optocoupler. That's this little black package right here. And what it is a IR emitter and a detector in one little package. So what you do is you power the LED on the one side, and then on the other side you actually have the detector, and if the detector receives light, it will allow a current to pass through itself because it's a phototransistor, and that will give you a logic level here, which we can use to control our MOSFET. Let's do a test. Okay, so right now on the input we have 0 because it's being pulled down. So when I push this button, it will light up the internal LED. Okay. Now that that LED is lit, this phototransistor next to it can pass current through itself. So when I push the button, it will cause this to register a voltage because the voltage is being allowed to pass through it and give us a logic level. So where I have my red lead here, this is what will actually go to the logic level MOSFET, allowing us to control it completely isolated from the main BeagleBone Black circuit. So as an example, like if there's nothing connected here, like if the BeagleBone Black is completely off, not connected to ground, floating basically, this will still be 0 because it can only be activated by light. Even if you have an integrated circuit that is not powered, it can still pass power through its pins if there is some power on it somewhere. The power can find a way through the circuit. So this is a really safe way to make sure that the latching solenoid is completely off.
Hey, so I'm designing a carrier board for our voltage regulator. It's a DC to DC regulator. It takes 3 to 30 volts in and then outputs 5 volts DC. So it's a buck boost regulator, and this is the board I designed for it. Probably gonna change a little bit on here, but for the most part, this is where the regulator will plug in, and then we'll have the battery connect here, a switch, and then these two connectors are for the BeagleBone Black, and the other one will go to the lock mechanism. This header is 5 volts, that's gonna go to the BeagleBone Black, and then these headers will connect. One is a signal from the BeagleBone Black and the other is a signal from the ATtiny, and they will turn on or off these MOSFETs. Oh yeah, I have another header on here for a jumper, but when I take this jumper off, I can get a current draw from the battery. So to do a test, I'll connect the battery and turn the switch on. We don't see anything light up. I have a jumper wire here. We'll connect the first MOSFET. Just make that high. Okay, the light indicates that it's on, so let's check the voltage. Okay, there's 5 volts. Now connect the other MOSFET. Give it 5 volts. Okay, looks like the MOSFET's on, and there's 5 volts. So this should work fairly well for our power circuit.
I'm going to use an ATtiny 45 to create the keypad entry program. Now the ATtiny is low cost and small, and it also uses very low power. I'm using AVR Studio here to actually write the code, and I created some of my own functions here, basically directional port. You know, you're probably familiar with Arduino and like digital write, but when you're programming in the tool like AVR Studio, you actually have to use the ports. So here's what's gonna happen. We're going to look for one of the 3 switches to be activated, and those are on the first 3 data lines of the ATtiny. And if they're in a certain sequence, as you can see, correct code, 1, 2, 3, 1, 2, 3, then we'll turn on the MOSFET, allowing the BeagleBone Black to turn on. And then the BeagleBone Black will undo the latch, allowing the system to be open so people can take selfies. All right, I'm gonna program it with the AVR Dragon. Let's just make sure we're connected here. All right, so that's our tool, our device, interface, okay. Let's read the device ID. Okay, so we got the device ID, which means we're connected. So the AVR Dragon has several different connection types, JTAG, high voltage programming. We're using ISP right here. And I made a little dev board with the ATtiny and a switch. And I even made a jumper here so we can remove the power indicator LED and get a true current reading when we try to go to sleep. All right, let's check the fuses. That all looks good. Okay, so our main loop, we're going to set the direction of each one of the pins. We have our 3 keys here. Then we have an output, which is the MOSFET, so we can control whether or not the BeagleBone Black turns on or off. Then the status pin is an input that's coming from the BeagleBone Black. The BeagleBone Black is a 3.3 volt LVTTL device, whereas this ATtiny, we're running at 5 volts. But if we're sending 3.3 volts into a 5 volt device as an input, it will still trigger as a 1 or a 0 because the 3.3 volts is above the 2.5 volt TTL logic level, which means it'll still work as a 1. You don't have to have it all the way up to 5. Here, port B equals hex 7. We're basically setting the first 3 bits to a 1, which enables the internal pull-ups. Okay, we have a timeout here, which is always decrementing. If it equals 0, then we turn off the light and we put the unit to sleep. The sleep is a really great feature on the ATtiny because when it's asleep, it draws very little current, like 0.3 milliamps, I believe. So yeah, we can extend the battery life by keeping it asleep most of the time. Also, we're gonna check the keys when it's running. So let's go down to the check keys here. All right, so it's gonna look at key 0, 1, 2, which will translate to key 1, 2, 3. If the key is pressed, which means if it's pulled down to ground, wait a millisecond for debounce and then wait for it to also be released. Then we'll put it into the entry code array, like the 6-digit code. We'll reset the timeout, so every time you push a key, you wake the system back up. It'll go to sleep after about 5 seconds, but if you push a key, it'll resume right where it was. And if we've entered all 6 digits, we check the code, else we increment the digit. Now down in check code, we compare the entered digits to the digit string, and if there's 6 matches, that means we did it, we entered the right code. At that point, we change the output of these 3 LEDs and make them outputs, and we flash them, and then we turn on the BeagleBone Black, which is the boot BeagleBone Black sequence. If we enter the wrong code, the LEDs will flash rapidly. Booting the BeagleBone Black, there's a slight delay. We turn on the MOSFET, we turn on the 3 lights to say, hey, you did it correctly. We blink them slowly. Then we wait for the BeagleBone Black to change its status line to a 1. Once that occurs, we then wait for the status line to turn to a 0, which means BeagleBone Black has turned itself off. We wait 15 seconds to just make darn sure the BeagleBone Black is off. Then we turn off the MOSFET, killing the power to the BeagleBone Black so it's not drawing any current. The BeagleBone Black, when it goes to sleep, it also has a lower current draw, but it's still way too high for this application. And then we reset the timeout, and then we'll fall right back to the main loop. Let's test it out. This is gonna be the 1, 2, 3 buttons, and the LEDs will blink when you push the button. That way you have positive feedback. So if you enter the code wrong, they'll flash quickly. After 5 seconds of not pushing buttons, the ATtiny will go to sleep to save power. But you can, let it go to sleep during the code pressing. When you push the button, it'll pick right up where it left off. So if you go 1, 2, 3, 1, 2, 3, this light comes on, indicating that the MOSFET is activated to turn on the BeagleBone Black. One advantage of the AVR Dragon over the AVR ISP Mark II is that you can do debugging. Let's look at how. Okay, I'm gonna go to the project manager, and here's my AVR Dragon, which is the tool we're using, but I'm gonna set the interface to debug wire. Okay, now that I've done that, I can go to debug, and it will probably give me a message, something like, oh, you're not set up for debugging. Do you want to set the fuses for debugging? Now, fuses are things on the microcontrollers that you can set permanently, so to speak. So I'm going to use this interface to enable the debug wire fuse. The thing to remember is once you've enabled it, you're going to have to disable it eventually. Otherwise, it's going to be trying to debug off the reset pin the whole time, consuming energy. Okay, disconnect the AVR Dragon from the target device, toggle target power, reconnect the AVR Dragon, and click OK. All right, so now we are running in debug mode. So let's take a look at the advantage of this. I'm gonna pause it, and it will show us exactly where we were when we paused. And we're in sleep mode. So I'm going to resume it and wake it up. Okay, now let's take a look. Okay, we're in the delay. This is really exciting. So we can actually step through this one step at a time by hitting the step button and see how the code advances. What's also cool is we can see the current memory map, the flash, the variables, and the pin states. Like if we go over here to the I/O view, we can take a look at port B, and this is actually what's on it. It's the output, the direction, and the input. It's pretty useful stuff. Here's the important thing. When you're done, you have to disable the debug feature. So I'm gonna go to debug, and I'm gonna go disable debug and close. So the AVR Studio is going to reset that bit, turning this back into ISP mode, allowing us to program it normally. Okay, I believe it's done. So now if we go back over here, we can change this back to ISP mode. And to double check that we did it correctly, we can go to AVR programming and just try to read the chip ID in ISP mode. And if we can, that means that we've turned off debug wire and we're back in the normal ISP mode. So yeah, that's one advantage of the AVR Dragon is you can do debug wire debugging and see exactly what's going on with your program, what the variables are, what the RAM is, where it is in the program, and pretty useful stuff. We've taken all of the components and combined them into one test unit. Okay, here's what they are. This is the power supply. Here are the batteries for the power supply, the ATtiny, the keypad, BeagleBone Black. And over here we have a few test LEDs and the opto isolator. So how the sequence will work when it's all put together, the ATtiny is always running. We just have an LED here just to let us know it's on, but we'll remove that because LED actually takes a lot more current than the ATtiny does while it's sleeping. So when you put in the code, the ATtiny will activate the MOSFET, which will allow the BeagleBone Black to turn on. Once the BeagleBone Black is on, it will send a 1 signal back to the ATtiny telling it that it's on. And the ATtiny will wait for that 1 to go to a low, and then it'll turn off the MOSFET. We also have another MOSFET controlling this motor, and this represents the latching solenoid or whatever unlocks the case. So we just have a little motor for now. You ready?
Yeah.
Here's the amazing code, 1, 2, 3, 1, 2, 3. Okay, it's booting up. And this should activate once this is on? Mm-hmm. Okay.
It's gonna initiate the GPIO and then send the signals.
Okay. There it goes. Okay, so there's a soft power button on the BeagleBone Black. When you press it, the BeagleBone Black will safely shut itself off. Once it shuts itself off, the status wire or the status signal that it's sending back to the ATtiny will go from 1 to 0. Then the ATtiny knows that the BeagleBone Black is off. I think this takes about 6 seconds to shut down.
Yeah.
So once it goes to 0, we wait, well, we made it like 6 seconds times 2 just to be super safe. Just so this thing is completely off before the ATtiny kills its power. So let's give it a try. I'm gonna shut down the BeagleBone Black. So this is shut down, but it's still running. Now it's gonna wait a few more seconds and then kill its power. Now that it's shut down, the ATtiny is sleeping at 0.3 milliamps, which means with that battery pack, it should last over a year in sleep mode. Of course, whenever you run this, you eat away at its life. Cool. Looks like everything's working. Now we just have to put it into a cool enclosure. Okay, so if we make this out of engraving plastic, it'd be kind of flimsy, so I think we should have an engraving plastic first layer and then surround it with 6mm plywood.
Okay.
That way we have something nice and solid to attach the spring to. And instead of like putting things into the case, I think we should actually build all of our circuitry around these panels.
Yeah.
So the circuitry will come down from the panel rather than be in the case. That way we basically put the panels into the case since all the wire is gonna have to go through here. See, we have the USB wire coming from the keyboard and we had to cut it, and then that would go into here. So once we put it through, then we'd have to rewire a plug on so it can go into the USB hub, but then we can't pull it out of this. So everything's gonna be tied to these plates. So I think we should start with the plates and then go from there. So my basic idea is we take the keyboard, put it in here like this, we put the code entry right above it, and then we build from there. So why don't you get the power wiring ready, and I will prep this first plate for keyboard attachment.
Sure.
Here's a laser cut plate for the inside. Let's see how it fits. Yeah, it fits pretty good.
Sweetness.
Okay, I want to have a wooden layer below this to give it some more rigidity, but we have to watch out for these lips here.
Yeah.
So I'm going to do something really cheap. Can you tilt this toward me so it's straight on? I'm just going to take a photo of it, and this will be like the cheapest, easiest way to get the measurements into the computer. All right. Okay. Here's the wooden frame. So this will attach to the bottom of the nice plate. All right, let's make sure this fits. There are a few deformations here. See these lips?
Yeah.
We didn't take those into account, but we did make the wooden frame smaller than the black plastic frame, so I think that should get us to the same result. Anyway, I have some little holes down here, which we can use as removal hooks, so we can put hooks in and then open up the system. We're gonna glue these pieces together, then we can start installing parts onto it. I made a hole to place the keyboard in. Look at that. So what I put back here were some general purpose mounting holes. So maybe if you could find some strapping material for the keyboard, and these will be a size 4 screw in the bin. And yeah, strap the keyboard in place. And while you do that, I will attach the buttons.
Okay.
Cool. I'm going to wire up the LEDs and switches on our panel the same way they were wired in our test rig. I've attached Velcro onto the underside of this keyboard, and what you do is you basically snap it in place. And this is pretty strong Velcro, so I don't think you'll be able to get this out without the hooks. This is the hook thing that I made. So basically, if you want to take it apart, you latch it into these holes and lift. There he goes. Okay, so I'm gonna need to roughen the top next. This is a panel I cut. This fits pretty well, but what I want to see is how much the camera actually sticks out. Because if I put this flush in the back of the unit, it's actually going to stick out a little bit. So what I'm going to do is press this into the frame. It should fit around it. There's going to be another piece of plastic covering it, but this is just the first piece. Now that fits pretty snugly. Okay, I'm going to cut a few more pieces for this, and we'll build the BeagleBone Black into it. I've got a piece of laser cut plastic here for the lens cover. Now I'm going to put the camera in place. We're actually going to have the camera oriented sideways. That way the USB sticks out the side and not out the top, which wouldn't work because we don't have enough room. Ta-da! Now let's put the BeagleBone Black in place. We've gone through the steps for each one of the components. Now let's see how they all fit together. Here is the ATtiny, which waits for the wake up code on this keypad here. This power supply keeps the Tiny going at a very low current. When the Tiny gets the correct code, it will activate this MOSFET, which will allow the BeagleBone Black to turn on, along with this LCD screen and the USB hub and the USB camera. And everything is powered by this 4-cell lithium-ion battery pack. So are we ready to put this in the case, Felix?
Yeah, let's do it.
All right. Oh yeah! Look, Felix, a geocache.
Yeah.
Wonder what's inside. Treasure, gold, spam. Oh, some sort of computer.
Knowledge.
Yeah, let's see if there's any knowledge. Let's enter the code. Oops, I entered it wrong.
That's not it.
Hey, okay, it's booting.
Wow, that was a complicated code.
I'm gonna tap the screen to start. Oh, here we go. Okay, so it took 4 photos, and then we can type a message that goes in between the photos. Cool, then it saves these as a disk. Mm-hmm. Nice. So the next person comes along. Oh, yeah, there it is.
Yep.
Oh, it's gonna do it again?
Yeah, just keep cycling through that.
Oh, okay, and then when we're done, we just close the lid and walk away?
Yep.
All right. And once we're done taking photos, the BeagleBone Black will shut itself off. Then once the ATtiny detects that the BeagleBone Black is off, it will kill all power to the system, go back to sleep, and then efficiently sip power until someone else comes along to wake it up. For this episode's challenge, we built a computerized geocache unit. Its power source is controlled by an energy-efficient microcontroller, which only wakes up the system when the correct code is entered. Once booted, it takes photos and messages, then returns to a power-saving state. The end result turned out pretty well. It was fun working with a low-power ATtiny 45. We did have to artificially weigh down the base to keep it from tipping over, and I kind of wish the screen had been larger. Of course, that would only make the tipping over problem worse. What would you have done with this project? Have you ever made or found a geocache yourself? What are some cool geocaching techniques that you enjoy? Let us know on the Element 14 community, where you can also keep track of our incoming episodes, builds, and special events. This looks like the perfect place to stash my geocache. It's more than 1/10 of a mile away from other geocaches, it's not damaging public property, and also it's not right smack dab in the middle of a trail or a hiking path where someone might trip over it.
Absolutely. It looks like the selfie cache has found its new home.
That's all the time we have for today. To learn more about finding this geocache in the wild and geocaching in general, go to element14.com. We'll cache you next time. What is it? So the real treasure is knowledge. Man, I sure wish my personal blimp hadn't have crashed. Then I went blimping. The Ben Heck Show is brought to you by Element 14, the electronic design community where you can connect and collaborate with top engineers from around the world. Join now at element14.com.